so my name is Nikolai, and I'm an engineer working in the developer technology group at NVIDIA. And so what this means is I work with developers like you on applications trying to port these codes to GPU and optimize them on the GPU. I'm going to use terms GPU and accelerators interchangeably because it's the same thing for us. So in this talk, I'll pretty much cover the architecture, very briefly overview of the architecture, some best practices, how can you program GPUs, and also maybe give you a bit outlook in the future, what we'll have. So first, maybe just some quick surveys. So how many of you actually done any GPU programming, anything like directives or libraries, or used like CUDA or anything? Okay. Pretty much 50-50, I guess. All right, so to get started, as I said, first, let's just cover some key points on the GPU architecture, and I'll also try to point you to some key things you need to look into your application to make it, to design it to work efficiently on the GPU. Before we deep dive into the GPU architecture, I'd like to first tell you that, give you a little bit of background on what is the heterogeneous computing in general. So all of you have your laptops, and all these, all the computers these days have mostly at least two different types of processors, so CPUs and GPUs. And they're actually completely different. So CPUs, they focus, and I believe you already had a few talks on CPUs before today. The CPUs, they mostly focus on serial performance. Each core on the CPU is focused on serial performance. And they have a lot of big caches. And really, they try to minimize the latency and try to get the work done as soon as possible on a given timestamp. Now, the GPUs, they usually have a different approach, and they focus on a high data parallelism. And what I mean by high data parallelism is that you have a lot of data, and you need to process it independently at the same time. And so really high throughput data parallelism is what GPU is focused on. And in your application, so heterogeneous computing means that you need to take advantage of both of them. So you need to, some part of your code might be better, well suited for the CPUs, and other parts of your code may be worth porting to the GPU. So you really need to take advantage of all the processors that you have in your system. Now, so what is the GPU architecture? So this is a very simplistic view of the GPU architecture these days. So the key thing to understand here is that GPUs have a few streaming multiprocessors. We call them SMs. And these multiprocessors connected over to some video memory or global memory or GPU DRAM through L2 cache. And then, of course, GPUs are connected over to the chipset through the PCI Express, and then also connects to the system memory. So typically these days, for example, in the Kepler K40 architecture, in HPC, this is the one that you'll probably see in Titan, for example. There are about 15 streaming multiprocessors, and the DRAM size in K40, for example, it's 12 gigabyte. So just to give you kind of a rough example of what it is. Now, if we go deeper, and so what is the streaming multiprocessor, or SM? So SM consists of a lot of functional units, and we call them CUDA cores. But essentially what they do some operations, and it can be a single precision floating point operation, can be double precision floating point operation. And these CUDA cores, so on Kepler, we have about 192 CUDA cores. What it means is that you can do about 192 single precision floating point operations per clock. And if you account that we have around 15 of these SMs, we get about more than 4 teraflop peak single precision instruction point. We get about more than 4 teraflops peak of our single precision performance. And then the double precision performance is about roughly third than that, 1/3 of that. So it's about 64 double precision floating point impressions per clock, and this account overall into more than 1 teraflop. So what else do we have on SM other than just the functional units? We also have some caches, a read-only cache, constant cache, L1 cache. We have a scratch space, scratch pad, we call it shared memory. And on these days, you can switch between different sizes. So you can have 16 kilobyte of shared memory or 48 kilobyte of shared memory and vice versa for the L1 cache. And there is also a large register file available for all these cores to work on. So this was just kind of very beautiful overview of the architecture. What is the execution model on these architectures? So the execution model is we call the CMT, which is a single instruction and multiple threads. What this means is you have a lot of threads running a single sequential program, but all these threads run in parallel. So you have a bunch of threads running in parallel. These threads are grouped into blocks, and we call them thread blocks. So threads in a block, they can cooperate with each other. They can have some synchronization with each other. They can exchange some data. And then also these thread blocks are organized into grid. So grid is a collection of thread blocks. And communication between different thread blocks is very expensive. So typically, all the thread blocks, they run independently from each other. Now, how this software execution model maps to our GPUs. So CUDA core, so all threads, they are assigned to CUDA cores, and essentially the thread block is assigned to a multiprocessor. So each multiprocessor can have multiple thread blocks assigned to it, and it needs to execute them. So thread blocks, they do not migrate between multiprocessors. So once you assign to a multiprocessor, you work on this thread block. And then to launch a function on a GPU, and we call these parallel functions kernels, to launch a kernel on the GPU, you need to specify a grid. So you launch the whole grid and put it on the device and then launch this kernel. So this is how the software architecture kind of maps to the GPU architecture. Yes. Another key point in our architecture that you need to understand is warps. So threads are also organized into groups of 32, which we call warps. And a warp is a kind of a single parallel execution unit, and all threads in a warp, they run at the same time. So they run simultaneously at the same time. So you can think of it like a lockstep execution of warps. And if we look at the thread block, for example, it can have, for example, 128 threads, and hardware see this thread block as a 4 warps, essentially, of 32 threads. And the warp is a very important term that is used in all the later best practices that I'll cover. So now, what is different between CPUs and GPUs? How they differ between each other? Kind of digging a little bit more into details. So CPUs, they design to minimize the latency, right? So they have big caches. They try to complete its work as soon as possible. And I have a simple example here. So let's assume we have some thread assigned to a core, and it needs to do some work, and then it needs to access some data. And so, and if we fall out of cache, so we need to wait for this data to arrive, and so we'll have some idle spaces. So the green chunks are thread doing some work, and then the white chunk is waiting for the data, and then the green chunk is doing some another work and waiting for the data. Of course, CPUs, they can switch to another thread, but the switching is usually very expensive. So the context switch is very expensive because you need to save the state of the thread and then load another state of the thread, load the state from another thread. Now, GPUs, they are designed completely differently. So instead of minimizing the latency, what we're trying to do, we're trying to hide the latency. So if we again look at the bottom chart here, we have, so instead of threads, we work on warps, as I mentioned before. So we kind of have the single execution unit is a warp. And so we launch our warp, and then we start with the warp 1 here at the bottom. We've done some processing. We submit requests for the memory, and we wait for this memory, right? And usually the latency to the memory is actually higher on the GPUs than on the CPUs. So you need to wait longer for that. But what makes GPUs really efficient is that you can actually switch to different thread at almost no cost at the same time. So instead of waiting for all this memory to arrive, you can actually switch to another warp, do some of its work, and then switch to the warp 3, and then switch to the warp 4. And by the time you actually finish the warp 4, the data will already arrive at the warp 1. So you kind of can hide all the latency for this memory requests. And this is what makes GPU very efficient, so that you, instead of minimizing latency, you're hiding latencies. It's very high throughput architecture. Now, so what happens if we say won't have the warp 4? So in this case, when we finish with the warp 3, we actually will wait some time until we get the data for warp 1, right? And so what happens if we won't have warp 3, then we wait even longer, so there will be even longer idle time. So what this means is that if you don't have enough warps, right, or enough threads, enough parallelism in your code, then you simply get GPU waiting on the data, and it will be inefficient. So, yeah.
So what makes the warp switching kind of cheaper than the thread switching in CPU?
That's how we design the architecture. So it's what do you mean?
So you mentioned warp switching GPU is much cheaper, much easier than thread switching in CPU.
Yes.
How does that happen?
Well, that's how GPUs work. So I mean, this is maybe we can cover this in more details later on if you have some particular questions. But it's just how the architecture is designed. So you don't have to store the whole state of the thread of each thread, and then load another state of another thread, because all the threads, they share the same program. So essentially, you don't need to do all this expensive context switching. So it's, I guess that can serve as an explanation, I think. But we can cover this in more details later if you have some particular questions. So rule number 1, expose a lot of parallelism and try to so accelerator threads are slower than CPU threads, and they also usually have lower clocks than CPU. So GPU cores, they have lower clocks than CPU cores. But we have a lot of we need to have a lot of threads, and we can work and we can hide them very efficiently, all the latencies. So the rule number 1, try to have to expose as many parallelism as you can in your code, and so fine-grained parallelism is good, and coarse-grained parallelism is bad, which is light thread, for example, for accelerators. Now, so I'd like to spend some more time. So obviously, you cannot cover all the optimization practices, how you can optimize, how you can design a code for the GPU to work better. But I'd like to cover some key points here. So what is important to understand about GPUs? So first thing, so once you expose the parallelism, so what's next? You need to think about the data locality and try to optimize the data locality. So CPU and GPU, they have different memory spaces. So whenever you're trying to run some program on a GPU, you usually need to copy this data to the GPU, run this program, and maybe if you need this data back, you need to copy the data back. So if you have, for example, some very small part of your application port, and it does almost nothing, just maybe some simple memory operation on some data array, you actually won't gain anything, because the connection between the GPU and the CPU memory, right? It's PCI Express. It's very slow. It's much slower than the way you can access the GPU memory. So the key thing here is try to minimize the data locality. If you can keep the data on the GPU longer and do some more computation with it, so that's useful. Try to design your program in such a way that you have some chunks of the program that executed on the GPU and doing some useful work in there, instead of just moving the data back and forth. Now, once you move the data to the GPU, you want to keep it as close to the streaming multiprocessors as possible. So, of course, accessing the DRAM is cheaper than accessing system memory and doing copies over PCI Express. But even cheaper is when you have your data stored on SM. And we have lots of different ways you can try to optimize for that. So you can try to store some intermediate data in registers, for example, instead of always copying them to the global memory. You can use shared memory, which is a special memory available in each multiprocessor, which you can store some data in and try to access it frequently. And then also you can try to take advantage of the read-only cache. And the easy way to do this with the compiler is just to specify the pointers with const strict. And so the compiler will usually use the read-only instruction for that. And this is just a few examples. I mean, there are lots of different ways you can optimize for the data locality on the SM. Now, assuming you moved as much data as you could to the SM and kept it there, but then still you need to access the global memory anyways, right? And so the key point here is you need to make this memory access as efficient as possible. And we have this term called async, which is you're trying to, so the warp consists of 32 threads. And each thread can access its own different memory location. And so what the hardware tries to do is tries to minimize the number of cache lines it needs to bring for all these threads in the warp. So if all these threads access the same cache line, then only one cache line will be moved. And so this is the best example here. So all threads accessing in the very nice aligned fashion. And for example, they access a single cache line. So in that case, only one transaction will happen. That's the best scenario. Now, what will happen if we have a scattered access from all the threads, or kind of a memory divergence in this case? So in this scenario, there will be 32 separate transactions for L1, and each transaction will actually generate an additional replay of an instruction. So not only will actually waste some memory bandwidth, right? So we'll have to bring more data than necessary because each cache line will be 122 byte, but also will actually generate more instructions. So SM will spend some time replaying the instructions then instead of doing some useful work. So this is not efficient, and try to reorganize your data, maybe realign your access in such a way that threads in the warp, they access ideally a few lines of the cache maybe, but not in a scattered manner as shown on the bottom. And speaking of divergence, so memory divergence is bad, and then also the warp divergence is bad. So what is the warp divergence? So our architecture executes warps instructions per warp. So if you look at the left part of the slide here, so we have all threads executing some instruction, and then there goes some condition statement. And then in this condition statement, only, let's say, 12 threads of the warp will enter the if statement, and then the rest will enter the else statement. So what will happen on the GPU is that in the first case, the whole warp will be actually executing this if statement. And so simply, the rest of the threads that are not participating, they will be idle and doing nothing. And then the else statement will be executed in the same fashion. So the conditional statements, if they depend on the thread index and diverge within a warp, they will be serialized. However, if this would not be 12, but let's say 32, then the whole warp will be executing the if statement, right? And then another warp maybe will be executing the else statement. And this can work actually with no impact on performance because we can switch between warps at almost cost-free, as I mentioned before. So try to avoid any divergence that you have within warps. And if you have any branching on the thread index, it usually can mean that. So try to avoid that. And just to kind of have a quick summary here for the best practices, so you need to expose enough parallelism for the GPUs to make them work efficient. Try to optimize for the data locality. First, move the data to the GPU, optimize for the locality on the GPU. And then, if possible, move the data closer to SMs by using registers, shared memory textures, or whatever we have there. And for the remaining access to the DRAM, try to avoid any divergence if you have. So try to have nicely aligned, or at least in consequent accesses instead of the scattered memory requests from within the warp. And Then also try to avoid any warp diversions that you have in the program. Okay. So now that we know a little bit about GPUs, so we can maybe go into how can you program them? So what tools we have to program the GPUs? There are 3 ways you can accelerate your applications on the GPU. There are libraries, there are compiler directives, and there are programming languages. Ideally, your program should probably have all of them in it because they differ in simplicity and performance. So libraries, it's something that somebody already wrote for you, and it's probably already optimized for this architecture, so you don't need to do anything specific about it. So you just call the library, use it, and that's it. So it's very simple to use. It's high performance. But unless it's something that people already done, for example, BLAS, FFT, or something else, you're probably out of luck. So you need to still re-implement it yourself. So you cannot find the library for anything that you do. So there will be something that you need to code yourself. So the next approach is to use the compiler directives, right? In this case, you can keep your code portable, so you don't need to modify your code. You only need to insert some directives for the parallel loops, for example. However, the trade-off here is that usually the compiler directives, they do not expose low-level details of the architecture. So it's not always that you can program your code very efficiently with the compiler directives, but they're still a nice and useful tool. And then there is obviously programming languages, which can expose a lot of low-level details to the architecture. But the trade-off here is that it's usually a very high learning curve, very steep learning curve of the programming languages. So sometimes you have time to learn them, sometimes you don't have time to learn them. So it's another option for you to consider. And I'll cover all 3 options, kind of what we have. I won't focus on compile directives because I will have the talk on Wednesday on this, so the dinner talk on OpenACC. So I'll just cover the libraries that we have and the programming languages. So for the libraries, there are obviously some third-party libraries available out there on GPUs, but I'll focus on a few NVIDIA libraries that we provide and that you can use, and they are surely optimized on GPUs, so you just can use them and you'll achieve the best performance on these particular tasks. So just to give you a few examples, we have cuBLAS, which is BLAS library. And to use cuBLAS, what you typically need to do in your program is just to replace all the calls that you have in, for example, TestXPy to corresponding cuBLAS API call, like cuBLAS-XPy, for example. Then you need to, sometimes you also need to manage the data locality. So you need to maybe allocate this data by using the CUDA calls or by using cuBLAS calls and move this data to the GPU. Sometimes you don't need that. Libraries can handle it for you. And the third step is obviously you need to rebuild and link with the CUDA library. Now, if you're actually lucky and you're using some level 3 BLAS routines, for example, the dense matrix multiplication, or I don't know, TRSM or something like that, you can actually use our drop-in library NVBLAS. You don't need to modify your code or even recompile it at all. And this library will use all the GPUs available in the system automatically. So all you need to do is just preload it using LD preload. So it will intercept your calls to DGEM and other BLAS level 3 routines, and efficiently tile the matrix, move it to the GPU, do the matrix multiplication on the GPU, move it back, and so it will be completely transparent to you, and you can achieve very high performance with that. We also have a few sparse matrix libraries. I'd like to point here, so cuSparse is good for SPMM, SPMV, these kind of operations. cuSolver can provide you with different LU, QR factorizations, and the interface is similar to LabPack. And the MGX library is a library, it's a algebraic multigrid solver library, which which is actually has a very flexible configuration, so you can specify different solvers. For example, using a GMRS solver with AMG as a preconditioner, and we have lots of different solvers available out there, and it's also MPI enabled, so you can run it on multiple nodes. Now, usually, sometimes you need to do some simple tasks like sorting or doing a reduction or doing a parallel scan, like a prefix sum operation. You don't need to code that yourself. We have a library for that as well, which is called Trust. So there are lots of, it tries to mimic STL, but it also has its own algorithms available out there. So you can try to use sort, reduction, or exclusive scan, or other algorithms. And it's actually very easy to use. So here is just an example how the code looks like in STL and C++ on the left, and then on the right is how the code looks like with using Trust. So you just replace std with Trust, and then you would also need to allocate the device vectors that will be on the GPU, and simply copy when you do the assignment, it will copy the data from the host vector. And then the API, all the arguments are the same for the transform call. Now, if you want to do a little bit more kind of low-level programming, we also have a CUB, which is somewhat similar to Trust, but it provides all these reductions and collective operations on a per block or per warp level. So if you need in your program to do a reduction in a block, in a thread block, or in a warp, for example, you don't need to implement it yourself again. You can just use CUB, which is the library available out there as well.
Would you like to say something to Magma, the development of Magma? Do you have any experience with that?
I personally don't have any experience with Magma, but I think it's similar to cuSolver. So I think you can use either Magma or cuSolver. So I think they provide similar API maybe, but similar functionality for sure. So which one is most suitable, feel free to use. Yeah. Any other questions on the? Sorry?
I've played around with it a little bit last summer with my code, but I don't have any experience with CUDA or those tools. And I know it's a fairly new development from the University of Tennessee, Knoxville. So I was just curious whether you had any experience with it.
Yeah, well, I haven't personally used it at all, fortunately. But I know it's similar to cuSolver. I mean, probably should also try cuSolver and see if that's maybe easier for you. I don't know. Okay, so any other questions on libraries? I guess over here.
I don't know if it's relevant or not, but does this work on AMD graphics cards?
No, I mean some of the libraries might be available on AMD, but these are the NVIDIA libraries that we provide, and cuBLAS certainly won't work on AMD card. They might have similar libraries available. I'm not aware.
So this is specific to NVIDIA graphics card, or what else?
So Trust, for example, you can use it with CPU as well. So you can use it as an STL. So you can specify the Trust host vector and then use the similar thing on the host. Or if you have an implementation for AMD or any other code, I guess you can use it as well. But all the sparse, the cuSparse, cuSolver, AMG, X, they are only NVIDIA GPU only. And as I mentioned in the beginning, there are, of course, lots of third-party libraries available. I'm not covering them here. So Magma is one of them, lots of others. And some of them can be maybe ported to other GPUs, maybe not. Okay, so yeah, compiler directives, I'll just kind of skip through the slides. So this is how you use OpenACC very briefly. And this is an example. So just pragma ACC, but I'll have a case study on that on Wednesday, more detailed, like how we can do all of that in details. So now to programming languages. So these are all the languages that we support on the GPU. There are a lot of them, Fortran, C, C++. We also support C++11, Lambda functions. Here's just an example code of how the serial code looks like in a C regular C application, and then on the right is a parallel CUDA code. And I'll just walk through this. It's hard to explain the CUDA in just like one slide, but I'll try to do this. So on the left side, we have a sexpy example, a serial function that just loops through all the elements and does the computation. And we call this function with arguments. We specify number of elements. We provide the pointers to the arrays and that stuff. So what's different in CUDA? So again, this sexpy function, we call it parallel, and then to tell the compiler this is actually a parallel function that needs to be executed on the GPU, you need to provide a declaration global, the qualifier global here, so underscore global, and then this function will be executed on the GPU. Now, instead of, so in the CPU, we have a single loop running across all this, all the computations. In the GPU, we have lots of threads executing the same instruction, right? So we have this function executed by like 1 million threads, for example, and each thread essentially executes one element, right? So we have the int I, we specify, we compute the index of our element that we want to execute, and we use the the block dimensions, thread dimensions. We compute the index, and then we do the computation, which is exactly the same as in the left side, and that's it. And then we need to call this function from the host. So this is where the triple bracket syntax goes into. So you specify the grid dimension, you specify the block dimension, and then you provide all the arguments, and there you go. So you can launch this program on the GPU. So of course, here you can run the program on the GPU, but how can you manage the data on the GPU? And so we have 2 ways you can do this in GPU, so in CUDA specifically also. So you can do explicit allocations by using CUDA malloc. So on the left side, there's a simple example where you read something from the file, and then you sort this file, and then you use this data somehow. And when you try to pour this thing to the GPU, you need to allocate the data on the GPU. You need to copy the data that you read from the file to the GPU. Then you launch your qsort or something else. Then you copy this data back to the CPU, use this data, and you also need to free the pointer. And you need to use it, in this case, you have to use a separate pointer, d_data, for example. But we also have another way which you can use on Kepler and with CUDA 6. You can allocate memory using the CUDA malloc managed. So you can keep the same pointer. You can access it from both CPU and GPU. And you don't need to explicitly copy the data between CPU and GPU, as in the example on the left. So the only thing you need to do is you need to call the device synchronize, which completes the kernel. So you need to guarantee the completion of the kernel before you can use the data. And that's it. So 2 different ways you can try to manage your data on the GPU. So the difference is in the first case, with the CUDA malloc, CUDA memcopy, it's explicit allocation and moving the data between CPU and GPU. In the CUDA malloc manage is a single pointer, so you can use a single pointer on the host and device. You don't need to copy it back and forth at your own. It will be done automatically by the CUDA driver. The trade-off here is that with CUDA malloc, CUDA memcopy, you can do this asynchronously. You can overlap this somehow if you want. With CUDA malloc manage, currently on current architecture, it has to be synchronous, so it only copied at launch of the kernel or whenever you try to access this data from the CPU after the kernel launch, after the kernel completion. And so obviously the first path is kind of more, you can achieve better performance usually, but the second path is simpler. So my advice to you is to try to use CUDA malloc manage first, see if you can make it work with your application, and then only then switch to CUDA malloc and CUDA memcopy for performance optimizations. Okay, so maybe just a few words on what's going to change in future, what the new technologies will have, and before I actually go there, are there any questions on the programming tools in general, like programming GPUs, libraries, or CUDA, or anything?
Well, if I wanted to do that and I don't know, you said there's a big learning curve. What type of program would I be looking at before I would want to go into learning how to program this? How long would it take me to?
So there is a big learning curve maybe for CUDA, and it's getting easier and easier. For example, here you don't need to learn about the CUDA malloc, and actually you don't need to check the data how you want to to copy to the GPU. It will be done automatically. So you can use libraries. You don't need to learn anything about the GPU architecture if you just use libraries. You can use the compilers, the compiler directives, and I'll have a talk on that. So it's also very easy. You don't need to modify your code in any specific way. You just need to add a few directives there. Is that answers the question?
Well, I was asking more about the actual programming, because yes, I'm really interested in the compiler directives part, because I think I can just throw that in a problem, but to actually learn.
Yeah, so we have the resources. If you're asking about any resources, additional resources on GPU or something like that, more like in examples or.
How long does it take a certain person to learn how to?
Well, I would say it depends on the person, but sometimes probably maybe a few days, or maybe that's. I mean, writing like this code, I don't think it will take you more than a few hours, or maybe. So it's usually not that complicated. The complicated part is where you start to do some optimizations, or you're trying to do some asynchronous, so you can trying to do something not standard that people usually do. So if you want to do like a asynchronous copying between CPU and GPU, trying to do some specific optimization with looking at the threads and trying to synchronize them, exchange some data using shared memory, for example. So these kind of advanced, techniques can take you a little bit more time to learn. But doing something simpler, this is not as difficult as probably doing a compiler approach as well, some sense. So compiler is probably easier because you don't need to take care of all these, indices. You don't need to compute it yourself, like here. And also you don't need to have a special, declaration of all these functions. But this is also kind of pretty simple. Okay.
So I'm not familiar with this at all, so my question might sound dumb. But I have an embarrassingly parallel application. I have ODEs, so equations I need to solve. Right now I just do MPI decomposition and allocate some ODEs to some processors. Would I benefit by using?
Yeah, so as I mentioned before, you need to expose a fine-grained parallelism. So just doing MPI and having few cores, MPI ranks doing something, might not be as efficient in your case. So you might want to, you're assigning some work to an MPI rank. You might want to decompose it a bit more if you can. Because if you just trying to run a few MPI ranks, how many parallelism, how many parallel threads you can get there, right? So it's also a question whether you're using any parallelism within an MPI rank, whether you have any OpenMP threads or anything like that.
Just have one processor solve a certain.
Yeah, so you need to expose more parallelism. So probably just trying to use an MPI rank and think it as a thread, it won't be efficient at all on the GPUs. So try to parallelize your application even more. So try to expose more parallelism in your MPI ranks. I'm sure you can probably do that, or we can discuss later on, see how we can do this. Okay, is there any question up there?
Here, hi. I remember that allocating a two-dimensional array with CUDA is quite difficult. So you need these pitches, and it's not a straightforward way that it is in C, just using an array of pointers. Can you explain why?
So the two-dimensional, you can allocate the two-dimensional array if you want. You can just use like a CUDA malloc and allocate a linear space, right? And then just use indices. So that's how you would do on the CPU also maybe. You can do this with this special CUDA malloc, I think 2D or something. That there is one special that you need to provide a pitch. Also, these are necessary to be able to use textures, I believe. So so we have some special texture instructions that you can do, like interpolation, for example, in hardware. So you don't need to do interpolation yourself in software. And if you want to do things like that, you might want to use this CUDA malloc 2D and the special allocators with which linear memory. But this is kind of an advanced topic, so probably can cover more kind of in one-on-one discussion. Maybe just a few new things that will be coming in the future. So we'll have a NVLink. So this is a high-speed interconnect between GPUs and between CPU and GPU. It's from 5 to 12x faster than PCI Express Gen 3. For now, the only planned support is for power CPUs, IBM power CPUs. Then the next big thing is HBM or stack memory. It is high bandwidth and high capacity memory. So the bandwidth will be up to 1 terabyte per second, and then the capacity will be almost up to 3x larger than the current generation GPUs. It is also more energy efficient per bit, so that you don't have to use more energy for that. Of course, there will be improvements in unified memory as well. So we have lots of limitations in Kepler and current GPUs. Future GPUs will support unified memory in a very efficient way. So there are improvements in software and in the hardware as well going in there. So it will be easier to use the unified memory. So you only have to have a single pointer. You can use it between CPU and GPU. And of course, big system for coming in a few years is Summit, which is IBM, NVIDIA, and Mellanox. So each node will have Power 9 CPU, multiple Power 9 CPUs, and a few NVIDIA Volta GPUs. There will be NVLink interconnect between all of them. Then also very large coherent memory space. And the performance in the applications that we expect to be is about 5x more than on Titan, current leadership system at Oak Ridge. So this is just a comparison chart for you to look into in more details if you want to see what particular numbers are different between Titan and Summit. So application performance, number of nodes, and such. So I'd like to highlight a few key differences just to kind of that are maybe relevant to you guys when you try to design your algorithms. So first, there will be fewer nodes, but they will be much more powerful. So on Titan, we have like 18,000, I guess, nodes. And then on Summit, there will be 3,400 nodes. But each node will be much more powerful. What it means is that you would need to expose even more parallelism per node than you usually do. And you would need to keep both CPUs and GPUs busy because both of them will have a very nice and a good performance. And CPUs are good for their tasks, GPUs are good for their tasks. So you need to keep them all busy. Probably use OpenMP or OpenACC programming model. But of course, you can also free to use CUDA if you want for low-level optimizations. It will have very large memory and relatively small increase in the bandwidth of the interconnect. So that's why, again, try to minimize any communication that you have between the different nodes and don't try to rely on that. Try to exploit as more parallelism as you can within the node. That's all I have. So I just wanted to highlight a few different examples, a few different links that you can go to and learn more about GPUs. So the CUDA Resource Center is everything you need to learn about the CUDA programming guide, API reference, everything is in there. Then the GTC on demand and webinars is a great set of presentations, talks, tutorials that we collected over the previous GTC. GTC is a GPU technology conference that we usually do every year. So it's a very great place to look for something that maybe already somebody done something similar that is related to your algorithm and just see what they've done with the GPUs. Parallel for All blog is a nice resource where NVIDIA experts share their pro tips on how you need to do something very interesting on a GPU, how you can do this. So it's a very nice thing to go there, check maybe some new things coming up there. It's not only NVIDIA, we also have some third-party customers doing some interesting blog posts there. And then finally, the self-paced labs. is a set of labs which are self-paced. You can just go there, take them, and whenever you can, and then just learn about GPUs. So it's completely self-organized. So you can do this every time. You don't even need the GPUs on your machine to do them. Yeah, that's it.